Welcome. This paper is about a single-layer, unidirectional, broadside-radiating planar quadrupole antenna for 5G IoT applications. My name is Rodriguez-Cano from Aalborg University, and I have done this work in collaboration with Professor Richard Ziolkowski from the University of Technology, Sydney. The advent of 5G has brought up many new IoT use cases for healthcare. The focus of this paper is on body sensors for health applications. Desirably, the antenna should have a low profile, flexibility, and unidirectional radiation pattern. The antenna examples that are shown in the images can be stuck on the arm, but they are quite bulky. Another popular solution is the Huron source antenna that combines a driven electric dipole and a pair of near-field resonance elements, the Egyptian dipole yielding the electric dipole response, and the two capacitively loaded loops, yielding the orthogonal magnetic dipole response. Their balanced combination produces the cardioid-shaped radiation pattern associated with a Huron source antenna. It is hard to obtain a flexible antenna when the loop includes vias that pierce the substrates. So the aim of this paper is to obtain a similar radiation pattern without piercing the substrates. However, without those vias, the parallel strips alone cannot achieve the loop current needed to form a magnetic dipole. Rather, a simple parallel strip combination can achieve an electric quadrupole. A typical quasi-Yagi antenna is shown in the top left of the slide. It is a configuration with one driven printed dipole and one parasitic strip parallel to it. Our studies found that the shape of the directivity pattern depends critically on the length of the elements. If they are much smaller than half wavelength, the directivity pattern remains the typical donut-shaped electric dipole one. On the other hand, when their lengths become closer to half wavelength with a small separation, a more unidirectional pattern is obtained. In order to reduce the large back lobe of the combination of two pairs, the proposed solution has only one driven element, which is centered between the two parasitic pairs. This pattern is clearly much closer to the desired cardioid shape produced by the broadside-radiating Huron dipole antenna. These are the simulation results of the proposed design, yielding higher gain than the Huron source antenna. A proof-of-concept prototype has been manufactured for operation near the GPS L1 frequency. The radiation patterns are obtained in the SATIMO near-field range anechoic chamber in Aalborg University. The measured radiation patterns show quite good agreement with the simulations. They confirm the unidirectional broadside radiating performance of the prototype. Thank you for watching.
Today I would like to share with you a dipole antenna with both odd and even modes excited and tuned. We usually use the half-wavelength dipole antenna. We could see that it actually resonates at odd mode. If the dipole antenna, the fundamental frequency is 1 GHz, we could see that it also resonates at 3 GHz, 5 GHz, and 7 GHz. What's the reason of this? We can see the input impedance for each mode. For example, the half wavelength, 1 wavelength, and 1.5 wavelength, the reactance is 0. But for the older modes, such as half wavelength, 1.5 wavelength, the resistance is low and could near to 15 ohm. But for the even older modes, such as 1 wavelength and 2 wavelengths, the resistance is very high, and theoretically it approaches infinity. So for this mode, they can't be matched. And if we simulate the structure without considering the feeding port, we can see that there are many modes evenly distributed in the frequency spectrum. But what we wish to is the excitation of both odd and even modes. Here I wish to introduce an exciting method, a capacitive coupling element. Usually it's a simple strip near the radiating structure, and the length is usually small. There is node in resonance, but if you place a CCE at a current minimum, it could excite the desired mode. First, we use the dual port scheme. We place one port exactly in the middle of the dipole antenna, and another port is also in the middle. It's attached to a CCE, and for this design, both odd mode and even mode could be excited simultaneously. And further, we consider whether we could combine these two boards into one port. Instead of the port embedded here, we use a narrow strip connecting the CCE and the main strip when the structure is in odd modes or in even modes. So we could verify all the first seven modes have been excited. And after the modes are excited, another problem is how can we tune this mode. Here we propose a method of indentations and protrusions. In this antenna, only need a pair of indentation at here, then it could tune this mode. But at the same time, it will not affect other modes. So that's all. Thank you.
This video is used to introduce a parallel folded dipole antenna. With enhanced bandwidth and compact size, it is a good candidate for millimeter wave wireless communications. Due to sharp variations in resistance, it is difficult to achieve wide working bandwidth for the half-wavelength dipole. Then, two half-wavelength dipoles are considered to be connected in parallel. The input resistance is significantly reduced, and a flat input resistance curve can be observed between two resistance peaks. This indicates that parallel dipoles features wide impedance bandwidth. An impedance bandwidth of approaching 80% can be realized when the port impedance is set as 70 ohms. To reduce the footprint, the terminals of the parallel dipole are bent inwards, constructing a parallel folded dipole. The bending terminals have only a slight effect on the input impedance. But the antenna footprint is reduced by 20%. The parallel dipole can be decomposed into two dipoles excited by a common mode signal. The relationship between voltage and current can be conveniently expressed using an impedance matrix, and the common mode impedance can be calculated. Considering the characteristics of the parallel circuit and network reciprocity, the input impedance can be further derived. It is clear that the input impedance of a parallel dipole is affected by the mutual impedance. Therefore, the spacing between two dipoles is a key parameter that affects impedance matching. Based on the concept of parallel dipole, a PCB-based parallel folded dipole is developed for planar integrated circuits. A simple feeding method is constructed by a coupling slot and two grounded metal holes to realize differentially excitation. Benefiting the broadband property of the parallel dipole, the proposed antenna realizes an impedance bandwidth of 64% from 16.7 to 32.5 GHz. About 1 octave band. For millimeter wave communication, a high-gain array antenna is necessary to ensure the link budget. The designed parallel folded dipole is expanded to a full corporate-fed 4x4 array by using a simple microstrip feeding network. An array prototype was machined and measured. The measured results shows an impedance bandwidth of 65%, a peak gain of 17.5 dB. Moreover, an antenna efficiency higher than 70% is realized. The measured patterns show good symmetry and low cross-polarization levels below. The proposed parallel folded dipole antenna exhibits good prospects for 5G millimeter wave applications.